we start thinking about the solution. We start the solution that the first thing that comes into picture. Yeah. So from so when we am I audible?
Yes, madam.
Yeah. So as we were discussing, so there are two. There in majority there are two types of devices. One is passive type of devices, another one is active type of devices. So when you look at passive devices, they are made up of passive components, and active devices are made up of passive components along with some switches. So due to the involvement of switches, we get a lot of flexibility. And why did we move from passive to active kind of compensators? Because the nature of our loads that are present have changed from time with time. Right now we are in era where we are thinking about electric vehicles and renewable sources of energy like solar, wind at a distributed level. That means at our houses and in our distribution system. So when we talk about these kind of systems, we have to think about dynamic nature of load. And since in a source load system, we have source and we have load. And in this source load system, when the load varies, then we need to put something here that take care of this varying nature of load. Initially, when the load was sort of constant in nature, we were able to do with this single source load system. But right now, because the nature of load is not the same, it has changed over the time. So therefore, we have to, in order to take care of these problems, what we do is, in order to take care of these problems, we try to put certain kind of compensators that take care of this variation in the load and make this overall system efficient. And in order to understand what kind of problems are there in the load, in one of the weeks we also studied about non-linear loads and how to analyze them, how to obtain the waveforms of these non-linear loads, how to obtain the RMS values of the overall waveform and the RMS value of the fundamental components. All these things we looked in one of the weeks. So we try to understand what are the problems with the load, and then we try to tackle it using passive and active compensators. Now, when we looked at the problems that are faced by the load, we looked at harmonics was one of the problems, then power factor lagging or leading power factor was another problem, and then because of these non-linear current flowing, voltage regulation was another power quality problem. So these are four of the problems that we looked at. Now we started with discussing about passive and active compensators, and the goal of these only compensators was unity power factor correction and voltage regulation. Then currently we moved on to the second part of this course where we are discussing passive and active filters or power filters, where the goal of these compensators is mainly harmonics or harmonics along with unity power factor or voltage regulation. So as such, there is not much difference in this terminology. The main important thing to remember here is the application and the basic principle behind which we are trying to design this equipment. If I'm taking a compensator I am connecting it in shunt with the source load system, and I am doing the harmonic compensation, then this will act like a harmonic filter. If I am having the same physical arrangement, and instead of harmonic compensation, I am trying to take care of the load power factor. Then this same shunt device which I am connecting can be called as power factor correction device. So the application or the goal with which this design is the design of this compensator is performed and the algorithm inside it. So there are two aspects. So when we have also discussed that whenever we talk about any kind of active compensator, then there are two steps. First is the design step, and then after design there is the control algorithm. One is hardware aspect, another one is software aspect. So whenever we look at any active kind of compensator, we first do the design of the hardware components present inside that compensator. So we find the value of the capacitor, we find out the voltage rating and the current rating of the switches, then we find out the L value of the inductor, which will be used for interfacing with the grid. So all these things come in the category of design or the hardware. So after designing the hardware, now we need to give signals to the switches. Switches are power electronic stat. These are dynamic switches which operate when certain electrical signals are given to them. So they operate corresponding to an electrical signal. So whenever I am using a switch, I have to give it a signal to tell the switch when to turn on and when to turn off. So these signals are generated using a block that can be called as the control algorithm block. So using this control algorithm block, I will sense certain inputs. I might sense the point of common coupling voltages or the load currents, ILA, ILB and ILC. Based on these few input data, my control algorithm block will calculate the gating pulses for these switches, and then that will be given to our hardware setup. And this control algorithm part, the most complex part in this control algorithm part is writing the software, and these software or these algorithms are written inside our DSP or control boards. So this is the overall system that exists in power quality improvement. So what I do is, whenever I am given, suppose this is my source, which is a three-phase three-wire source, okay, and I have a likewise three-phase three-wire load. Then, if I draw my source load system as this, suppose there is a three-phase three-wire star connected load. Now I have certain goals. Let me say I want to do power factor correction. So I will take a three-leg converter, that is the hardware. I will take switches, I will take DC link capacitor, I will take interface inductors. Again, this I am taking three-phase three-leg converter. You could take any other topology as well. So what kind of topology you are going to use for this three-phase three-wire problem also is a variable that you need to find out for your application, which is the most cost effective topology for your particular system, and what is the availability of switches or equipment around you. All these things will play a very big role in determining what kind of topology you are going to use at the end of the day. So let me say these interfacing inductors are of value N, this DC link capacitor is of value C, this is my switch S1, S2, S3, S4, S5 and S6. This is the hardware that I will be connecting. So in the physical system, all these things will be present inside a big box that we have been looking. We have looked at few images of the compensators, right? So this will be that compensator. So this will be a compensator box. In this box, this hardware will be present. Now, in order to control this, we will need a computer, or we will need a box inside that will have control algorithm inside it. Let me say I am using a DSP, that is a digital signal processor, for generating the gating pulse for these switches. So I have to generate the gating pulses for these switches. If I'm using this control algorithm block, then I have to give certain inputs to it. So let me say that this is VSA, this is VSB, this is VSC. These are the voltages at these nodes. Let me say I'm sensing these voltages. Then let me say I'm sensing these currents also. ILA, ILB, ILC. All these inputs that I'm sensing, I will give it to the control algorithm block. VSA, VSB, and VSC, and then ILA, ILB, and ILC. So all these inputs I will give to the control algorithm block, and then control algorithm block will in return try to find out the gating pulses that will be given to the switches based on the algorithm that I am going to select. So we have discussed a lot about control algorithms as well, right? We have talked about a lot of unit template algorithms, synchronous reference frame algorithm, DQ frame algorithm. So you could choose any algorithm, and there is no way of saying that this is the best algorithm. We have to look at a particular application, and based on that application or the target, we decide which is the best or the most suitable algorithm for our case. So we find out the suitable algorithm using simulations, and then based on that we do the final implementation. And then this is your whole system of the compensator. So this whole system is present inside the box that we have been looking at. So in this series, the box that we'll be looking at will be an active series filter. That means again switches will be there, passive components will be there, but the filter is connected in series. So this was a shunt filter. In this week's class, we'll be looking at series filter. That means instead of connecting in parallel to the line, the filter will be connected in series with the line. And in order to connect in series, if we just directly connect something, then it will be non-isolated, right? And if we connect any non-isolated, or if I directly connect anything, if I have this, suppose this is my single phase AC circuit, and I'm connecting a resistor in series to my load, and this is non-isolated connection, right? I'm directly connecting. Then in case this resistor is damaged, then my circuit becomes open circuit and no supply goes to the load. But since I am doing power quality improvement, I don't want my power quality, I'm doing an extra thing, right? I am the first thing that I need to make sure is my power supply should be continuous, or the continuity of supply. That is the most basic thing, right? If I am putting a very nice quality compensator, but I am able to give the power supply for only 5 hours out of 24 hours, there is no use, right? Instead, a customer would prefer that the power supply should be given for 20 hours, even if it's a bad quality supply, right? Most of us will prefer that. So the first thing that we need to take care is continuity. So instead of doing a direct connection, what we do is we use a isolation transformer, and then we connect the load, so that any kind of fault in the power quality improvement device does not affect our power supply to the load. So this is our circuit of a series power filter. So in the series power filter, we do this kind of isolation line. So this is our isolation transformer. Then on this side of the isolation transformer, I will connect the same topologies. Again, what we have been discussing, the topologies will remain the same. Only their connection to the system. Whether I am connecting this system, so this is again our full bridge converter, right? We have been discussing it. So the same full bridge converter we can use as a shunt compensator when we connect it here, and same voltage converter can be used as a series compensator when connected here. Only what will change? Only the control algorithm part, or the gating signals that we are giving to these switches. Only that will change. That whole part comes in the category of control algorithm. Okay. So this week we will be discussing this active series power filter. So let us get started with that part. So as we know that it is a series filter, and we know that whenever we have series filter, we take care of power quality problems which are related to voltage. So voltage power quality problems are like sag, swell, voltage imbalance, flickering of voltage, transients, notches, fluctuations, distortions in the waveform, there might be imbalances in the voltage, and there might be harmonics. Harmonics is the one of the major voltage power quality problems that is faced by us. So active series power filters is one solution to take care of these harmonics. So so I have been telling you about the system, right? The system that we were discussing, this blue box. This blue box looks like this. Looks like this. This after implementation. So inside this box, what all things are present? Now you know. You have hardware, switches. Yes, sir.
And these filters mitigate that reactive or compensation, madam. Filters.
Yes, sir. So depending on what application we are targeting. So we have been discussing about both in shunt, when we were discussing shunt filters. We discussed about the case of design of shunt filters for both harmonic and reactive power compensation, right? And for individual cases as well. So depending on what kind of design is being done. So this manufacturer, this multi-dialogue manufacturer, whether these people are designing it for, they can design it for harmonic or for reactive or for both. So it depends on what they are supplying. But you can do it for
Is
in
there any similarities or madam? Any similarities or differences between DVR and series power filters, madam?
so DVR is a kind of series power filter only, right? The only
Kind of series
change,
power filter.
yeah, the only difference between the two is DVR. Basically, both are connected in series, right? So that part is common first of all. Secondly, DVR. When we were studying DVR were focusing only on voltage regulation, right, or unity power factor correction. Whereas these power filters here we are trying to correct. Here we are trying to take care of voltage harmonics. So similar to what we have been doing for shunt, we started with shunt filters or shunt compensators, and those shunt compensators were taking care of only reactive power compensation initially when we started, and then when we studied active shunt compensators, we started doing harmonic compensation using them, right? So again, similarly we are doing, we just, these are just terms, but can you say that the active series power filter, which suppose this multi-dialog people have made an active series power filter, so they might also the same filter might also be taking care of harmonic this reactive power compensation. So you have to look in the manual or some kind of document of this product. What specifications are this product targeting? So these words you can just, these words you can just use it for theoretical purposes. But when you talk about practical, you can do the purpose of both reactive power compensation as well as harmonic compensation using the same device. They need not always be different when you look at the practical equipment. Okay, so in theory we just study them separately, because in order to simplify the understanding, if I put all the problems together of reactive power compensation and harmonics, then it might be a bit confusing. That is why we study one by one in theory, but in practical one device can take care of both the problems. It depends on the manufacturer. So when we look at state of the art of active series power filters, they are able to take care of voltage harmonics, voltage spikes, sag, swell, notches, terminal voltage, flickering, and unbalance. All these things can be taken care at once. And similar to the classifications we have been studying so far, these filters, active series power filters, can also be categorized based on the type of converter or the topology or the number of phases. So based on the type of converter, we know that there are two types of main converters, which one is voltage source converter, another one is current source converter. So based on this type of which converter I am using for which application, I can classify the active series power filter. Then another basis of classification is based on the topology, whether I am using a half bridge or a full bridge or a 3-leg converter or a 4-leg converter. So all these topologies that I am using, one classification could be done based on that. Another common basis of classification that we have been discussing is on the basis of number of phases. So whether my system is a single phase system or a three phase three wire system or a three-phase four-wire system. So all these factors are the basis of classification. So there are majorly three bases. So when we talk about first basis, that is converter type. So I could use either a current source converter or a voltage source converter. So this is an example of a current source converter because in the DC link inductor is connected. When in the DC link capacitor will be connected, it will be a voltage source converter. So we have already discussed why we prefer using voltage source converter compared to current source converter. So we won't be repeating it again, but you should, whenever you look at these lectures or whenever you revise these topics, you should keep on asking the question to yourself so that you keep on revising and you remember it with time. So, as we have already discussed, voltage source converters are much popular and much popular to be used because of few reasons, and therefore in our course also we will be looking at voltage source converters, numericals which are based on voltage source converters only. They are lighter, they're cheaper, they're expandable. And then we talk about when we talk about topology classification based on topology, then then the filter that I am connecting could be a half bridge filter, which is present here, or it could be a full bridge filter with four switches. So depending on whichever topology I want to use and my app is suitable for my application, I can go for any of these topologies. Then we'll go to the third classification, which is based on a supply system. It could either be a two-wire system or a three-phase three-wire system as shown here, or it could be a three-phase four-wire system as shown here. So for three-phase four-wire system, again, I could do a topology-based classification where I could use a four-leg converter, or I could use three full-bridge converters for each phase for independent control. So there are a lot of permutations and combinations available of making any kind of system, and we decide which system we will use based on particular application and expertise. Now, when we talk about the principle of operation of series active power filters, we know that these filters are connected in series using coupling transformers. When we talk about the voltage fed loads, which consist of capacitive filter and an equivalent load at the DC link of the three-phase diode rectifier, a series active power filter alone can effectively maintain sinusoidal supply currents. And so voltage fed loads and current fed loads, we have already been discussing these things, right? So voltage fed loads are the one whose output is sort of fixed, or there is a capacitor or a voltage source attached at the output of these kind of loads. So they are called voltage fed type of load. When the voltage is fixed at the output, we know that the direction of current will change, right? And when we know that the current is varying in nature, we need to take care of current power quality problems. Similarly, we can say the same about current, and you can apply the same analogy to current fed type of nonlinear loads. Now, the control algorithm for series active filter to eliminate current harmonics is suitable for both series active filter and hybrid configurations of a series active filter. And for voltage sensitive loads, to eliminate the voltage harmonic unbalance and maintain zero voltage regulation at point of common coupling, series active power filters is directly controlled to inject sufficient voltage in series with the supply. So this is an example of a voltage fed load, because at the output of this diode bridge rectifier a capacitor is connected, and due to this presence of this capacitor, we call this load as voltage fed type of load. So since this is a voltage fed type of load, I can model it as something like this. Now, in order to do the if this is a equivalent circuit. Now, if I want to take care of this voltage, what I'll do is I'll connect something here. Let me say I'm connecting a voltage source here. So this is our VC. So from where the logic of active series, this is showing the logic from where the evolution of series power filter came. Series power filter are nothing but KVL, Kirchhoff voltage law. So we know that in order to take care of these harmonic voltages or any problem in this voltage, we can connect something in series to make to make the net combination of desired voltage. So in order to obtain that, we knew that we need to connect something in series. So this something is called as active series filter. And what exact value of active this compensator voltage are we going to present in our circuit? That depends on our application. What we are targeting right now. So if you look at this system, then the goal that we are trying to achieve using active series filter is sinusoidal source currents. So in order to make the current sinusoidal in nature and unity power factor corrected, we need to give these kind of load voltages. And in order to give these kind of load voltages, when source voltage is of this nature, we need to add something or subtract something. So this Vf plus minus Vl is equals to Vs. So this Vf, because of introduction of this Vf, so Vf is basically filter voltage. So this is the voltage waveform of our active series filter. So based on this voltage waveform given by our active series filter, our VF, our VF injects voltage such that the load voltage is like this in nature. And when load voltage is like this in nature, our source current automatically becomes sinusoidal in nature. So this is the goal or the principle of operation of these active series filter. Now let us look at the analysis and design of these active series filters. Now once I know that I need something, then how do I find the value of this something? I cannot just put a random value to any system. I have to do the design first based on the worst case scenario. Now, let us say I want to design a three-phase three-leg kind of converter. So this is our three-phase three-leg converter which has interface inductors, DC link capacitors, switches and coupling transformers. So let me see how do we calculate the parameters. So suppose there is a three-phase 415 volt system. Since it's 415 volt, 415 by root 3 is 239.6 is the phase voltage. Suppose 25 kilowatt of nonlinear load is connected to this system, and switching frequency of the compensator that I am connecting is 10 kilowatts, and inductor current ripple is 5%, and DC link voltage is 700 volts, and the variation in DC link voltage that is per minute is 5%. Now, when we look at the design of voltage source converter of series active power filters, it is based on the DC link voltage of the three-phase rectifier load. So we know that the line-to-line voltage of the system, fundamental component of the load AC voltage is given for this three-phase three-leg converter. This expression is valid. We know that very well, right? And we also know that the line-to-line voltage of our system is given as 415 volt. So from this we can calculate the value of VD as 540 volts. Now from that we can calculate the VD is the value of the DC link voltage that we want at the output, this voltage. So based on that value of VD, using that VD, we could find the value of filter voltage. And this filter voltage, the RMS value of this filter voltage can be found out as this. And why are we doing this? We are just using the KVL again. So in the KVL, we know that there is our source voltage, then there is some filter voltage, VF, and then there is some load voltage, right? Let me call it as VF, and this is VF and this is VF. Here is the load voltage, this is the supply voltage. So we know that when I want to find VF, VF is equals to Vs minus VL, right? So when I look at the waveforms of this particular case which we are discussing, this particular case, when we look at the waveforms, we have already discussed that for a three-phase direct bridge rectifier, we obtain a stepped waveform, right? And this stepped waveform is Vd by 3, 2Vd by 3 and 2Vd by 3. Okay, so these are the amplitudes. We have already discussed that for a three-phase direct rectifier. So based on that, when we use this equation, this is Vs minus Vl, Vs minus Vl, Vs minus Vl from 0 to pi. So for each interval, since value of VD is varying, therefore we had to write different expressions. So this is an expression of basically calculating the RMS value of the active series vector. So using this in the numericals that we are going to discuss, we will again be discussing these points as well. So this is how we can find the value of the filter voltage. Now, now in order to find the value of the line current, we know that the line since it's a series circuit. In a series circuit, the load current will also be equal to the current that will flow through our active series filter. And since it's a series circuit, what we do is we calculate the load power from somewhere. And based on the load power, we can calculate the value of the supply current. And this supply current will also be equal to the current rating of the filter. And from this current rating of the filter, IF, and this voltage rating of the active series filter, we can find out the kVA rating of our active series filter. Now, when you have to, next step in the design process is deciding the rating of injection transformer or series active power filter. You can call it injection transformer or you can call it a coupling transformer. So in this coupling transformer, what happens is you need to take, in the design of a transformer, the two important things that you need is the voltage rating on the two primary and secondary sides of the transformer and the turns ratio of the transformer. So in order to find these two things, what you do is you divide the voltages on the two sides. So in this diagram, there are two sides. One is the supply side, another one is the voltage source converter side. So in order to design this transformer, you find the voltage which is needed at this point. So we just found out that the value of VF that we need on the supply side is 75 volts. So now I know that on this supply side, the maximum voltage that I need my transformer to give is 75 volts. Similarly, for voltage source converter side, using the DC link and the modulation index formula, you
Generally, supply side means this side, madam. This side, if you are saying this is load side, madam, not like.
can also supply.
You are saying this.
Supply means our source load system side and voltage source
Okay.
converter side.
Okay.
Okay, so it's for this transformer. This is our injection or coupling transformer. So there are two windings, right? One winding is on supply side, another winding is on the voltage source converter side. Okay, therefore I am calling it supply side and voltage source converter side. So now for as we were discussing, for the supply side we already calculated the value of voltage that was around 75 volts. Then for voltage source converter side, we could use the formula for modulation index and we already calculated the value of VD. That is the DC link voltage, which is 540 volts. So based on these two values, we can use our formula of modulation index, which is this. And using that, we can find out the voltage that is needed on the voltage source converter side. So the turns ratio for the coupling transformer can be found out as voltage source converter side to supply side. We know that N1 by N2 is equals to V1 by V2 for a transformer. So using that standard equation, we could find out using both the voltages. I was able to find out the turns ratio of the transformer. Right? Now, the next part to design is the DC capacitance value of the series active power filter. Now, since we know that the topologies are same for all kind of compensators, the only thing that is going to change here is the value of these parameters. The rest, everything is same. We have to find this DC link minimum that from the delta VDC that we told that minimum of 5% can be divided to 10%. It's a design problem. So you can whatever is the need for an application, you can decide your VDC minimum to be that. And using this energy balance equation and putting the value of VF and IF that we had just found out in the previous para, you can use it in this equation in order to determine value of CDC. This CDC that will come out of this equation will be some value that might not be the value of capacitor that is easily available in the market. So, as discussed before, what we do in this case is we try to find out the value of capacitor nearest to this available value. So, if I want 33 0.4 microfarad, and since it's a very specific value, it might not be available, so I'll go for a 4000 microfarad capacitor, which is easily available. Okay. Next, after design of DC capacitor and switches and everything, the next thing to design is interfacing inductors. So for the design of interfacing inductors, again, this is the standard equation that is present here, and using this standard equation, we can find out the value of interface filter by putting all the values that we have been finding out. Again, the next thing that we design is the ripple filter. So we have been looking at the design of ripple filter and its purpose. So again, what the purpose of ripple filter is to take care of the switching harmonics that are present at the point of common coupling. So when these problems are present at the point of common coupling, what we do is we use a ripple filter, and this ripple filter absorbs all the high frequency components of this system. And the equation of ripple filter is 1 by 2 pi RC. And by adjusting different values of R and C, you can find out the value of the switching based on the switching frequency. You normally set it to half the switching frequency. Suppose the switching frequency in my given case is 10 kilohertz. So I'll set the cutoff frequency for the ripple filter as half of that, so that it removes all the high frequency components which are present above 5 kilohertz. So we can select different values of RR and CR based on availability, and from that we can find out we can design the ripple filter. It's just one equation, two variables. So you can put different values of RR and CR depending on based on availability and design the cutoff frequency of this filter. So this is how you design any kind of series power filter. Now, when you look at the control part, we have been discussing a lot of control algorithms in order to generate the gating pulses of the switches in our hardware system. So, if you look at the control algorithm block diagram for elimination of voltage harmonics, then what is happening here is, since we are targeting elimination of voltage harmonics, what we do here is we compare the voltage sense to voltage signals with the reference voltage signals, and use these signals. The difference of these signals is used to generate the gating pulses. Now, from where do we get the load voltage reference signals? In order to generate these reference signals, we start with the supply voltages. We know we can find out, easily measure the voltage at the point of common coupling. So we find out these voltages, and we find out the value of load currents at that point of common coupling. And using the PLL, that is the phase lock loop that we have been discussing, we can find out the angle at which these phasors are rotating. And from these sin theta and cos theta values, we can convert the ABC, the measured quantities in ABC domain to DQ domain. Now, the signals or the parameters that are obtained in the DQ domain will have both DC and high frequency component. So, in order to filter out only the DC part, that is what we need, we put a low pass filter here. After obtaining the DC components of the D and Q part of the load voltage, we will add certain parameters or subtract certain parameters. Why do we do that? So the first reason of doing that is we needed to maintain a constant DC link voltage. If my DC link voltage is not constant and I am continuously discharging the capacitor, then the behavior of my system will not remain as desired. So we need to make sure that the DC link voltage is maintained at a constant level. So in order to maintain the DC link voltage at constant level, we add this part of the system. Apart from that, we also know that there is point of common coupling voltage, and we can take care of voltage regulation at this point of time. So in order to take care of that part, we try to maintain the point of the average voltage or the net voltage at the point of common coupling, so to be around say 230 volts. So in order to maintain the terminal voltage or the point of common coupling voltage, we add this to it, and this gives the Q part of the voltage that we need as reference. Now, by adding a separately respectively, we obtain the reference components in BM frame. But we need three-phase components. So therefore, we again transform this DQ components to ABC components and obtain these reference voltage waveforms. So this is how we obtain these reference voltage waveforms. Then we compare it with the actual voltage waveform, and using those comparisons and the PWM method, we are able to generate the gating pulses for the voltage source converter. And in order to look at the equations involved in the system, so again, all the system is broken down in the form of equations for you to understand it properly. So again, as I mentioned, the D part of the supply voltage has both DC and AC components, but I need to get DC component. So in order to filter this DC component, I use the low pass filter. What does a low pass filter do? A low pass filter has a frequency response of like this. It will filter the DC component, which is of 0 hertz, and it will filter out the AC components, which are present here. So it will help me extract only the VDDC part out of VSD and remove the VDAC part. This is this low pass filter. Using this low pass filter, I was able to obtain VDDC and VQDC part from VSD and VSD. So now to maintain the DC bus voltage, a PI controller is used at the DC bus of the voltage system. These are the equations for the PI controller. We estimated the V loss, and we also estimated the VQ component required to maintain the load terminal voltage. Using the reference D and Q components, EQ0 components, we were able to transform them into ABC domain and obtain the reference ABC components. So this is what this diagram was representing. Okay. Now there will be other algorithms. So the previous algorithm that we discussed was for elimination of voltage harmonics. Similarly, I could target current harmonics and generate gating pulses for my system using this block diagram. So the block diagram, the working of the block diagram could be understood in a similar pattern. There is again this terminal voltage maintaining loop, and there is again the DC link maintaining loop. There is again this ABC to DC domain transformation. Again, we are sensing the load voltage and load currents. The only difference in the two cases is that here, since voltage harmonics are present, so I use load currents in order to determine the positive and negative value. Whereas, in this case, since current harmonics are present, I am using the load voltage values in order to determine the sin theta and cos theta components. Using these components, I am able to transform my ABC domain signals into the DQ domain signals and obtain their low power and obtain their counterparts. This is how we can generate a gating pulse for our system. These are again the equations for the same block diagram. If you look at the block diagram and then you look at the equations, you will be able to understand the system very nicely. Then there is another control based on unit vector generation for elimination of current harmonics. So as we have been discussing, there are a lot of options and n number of control algorithms that are available in literature, and based on our application, we can find out whatever suits us. Then if you look at the simulation of one of the system, this is a 3-leg system, and in this 3-leg system, you can see that there is VSA, VSB and VSC, and then there is 3-leg converter with DC link capacitor, and a linear load is connected to the system. If you look at the distorted, if we assume that the voltage at this point is distorted, then you could see that due to the presence of this filter here, even though our source voltage was highly distorted in nature, our load voltage is nicely sinusoidal, and because of that, our source current and load current are also sinusoidal in nature. And they all are sinusoidal in nature. Why? Because of the presence of VF. If VF wouldn't have been there, or the series filter wouldn't have been there, then our VS or the load voltage would have looked something like this. And similarly, our load current and supply current, everything would have had harmonics. This is the advantage of using the active series power filter. And if you look at the harmonic content. Then the load voltage, if you look at the load voltage waveform, our load voltage would have looked something like this without the presence of series power filter. And the THD in this particular case, if you measure, it comes out to be approximately 19%. Whereas, when after connecting active power filter, our load voltage looks sinusoidal in nature and the total harmonic distortion reduces from 19% to 0.5%. This is the advantage of using active series filter. We are drastically able to reduce the THD of the load voltage that you can observe in this diagram. Similarly, if you look at the elimination of current harmonics, then in this particular diagram, you will see that there is source voltage and then there is load voltage. Then, because of the presence of active series filter, we are able to obtain sinusoidal source and load currents. If active filter wouldn't have been there, these currents would have been nonlinear in nature. So by injecting this weird waveform using the active series filter, we are able to obtain sinusoidal source and load currents. So this is the reason. Again, if you look at this particular.
What about VL, madam? VL is not no need of sinusoidal, madam.
Can you please repeat?
VL in this waveform, VL is like a step, madam.
Yes, I think since the nature of load here is non-linear, so we cannot take care of both the things simultaneously. For initially, our nature of load was linear. Therefore, we were able to obtain both load and sinusoidal currents as sinusoidal. But when nature of load is non-linear, in that case, we can take care of only one quantity at a time. So, using series part, our main goal is to take care of current.
Okay.
Okay. So if you look at the current here, in order to compensate the current harmonics, initially the harmonics that are present in the current were 61%. And then using the active series filter, I was able to obtain a waveform with total harmonic distortion of approximately 3%. So we reduced the total harmonic distortion from 61% to approximately 3%. So depending on whether your application has dominant current harmonics or dominant voltage harmonics, you decide which kind of compensator to use and which algorithm to use. So those starting points comes from the particular case. So on those starting points, you decide which kind of series filter you need. Okay. So the series filter that you can see here is for current harmonic compensation. Then there is one case in which the DC link of the load and the DC link of the active series filter are connected. This is a special case. So in this case also we obtain the same similar waveforms, but you need to take care of these kind of connections whenever you are doing. Except the DC load voltage is the advantage of this kind of topology is initially what we were doing is in order to maintain the DC load voltage we had a loop, right? We were comparing VDC reference with VDC and then a PI controller. So that loop is removed now. Since I am using this connection and connecting these points with these points, so because of that connection, what is happening is my output DC link voltage is fixed, and because of that fixed voltage, I don't have to put a additional loop for VDC comparison. So my DC link is already fixed. So this was about the theory part of active series filters. Now we can move on to the numerical discussion. Any doubts in the theory part?
No, madam.
Okay.
Madam, I posted one message to your email, madam.
Yes, I got your one of your mail recently. It is
Yes,
regarding
madam.
that
Yes, madam.
assignment 8 question, right?
Yes, madam. Yes, madam.
So I asked you last time to post that problem on the this discussion portal.
Al-
Did you get any response there?
uh, no response, madam.
Okay. Normally they respond, right?
No, not responding for yeah, even one time also, madam. Not responding, madam. Discuss forum.
Okay. Okay. I
Uh,
will. Okay.
I think.
Did you have you tried informing the NPT people regarding that?
Yes, madam. That discuss posted so many members, madam. Posted so many messages, but
Okay.
even though you are not getting one reply, also, madam.
So is it happening with everybody? Like none of they haven't replied anything yet. So far, no problems.
Yes, madam.
Because
Yes,
if
madam.
I remember last time in few lectures, a few people have mentioned that they got reply on discussion forum as this. Some,
Only first two assignment, second assignment only they are replied, madam. After that, no reply from that side, madam.
okay. So
Only first or second assignment.
okay. So maybe they might be occupied. Hopefully they will get back. So they have the duty of replying to those messages. So mostly they will get back to you because since I am not the one preparing the questions, I cannot actually there is a query inside that, and until I have a discussion from those who have prepared that question, I cannot provide you a solution to that question. That is the issue. That is why I told you in the last class also to ask
Same
ask.
model problems you are telling, madam. Same model problems.
Sorry.
The same model. What I am my ambiguity in what I am that questions are that also taught by you, madam. Also during problem session, you are also solved by the same problem, model problem solved, madam, already.
So that problem you can refer to the lecture that we have already solved. So do you have any problem in the
Same also
lecture?
in Bhim Singh sir lecturer also like that, madam. But they are writing ISH by IS1A, madam. THD IS is equal to. But they are writing the formula ISH by IS1 only.
Okay, the definition of total hormone distortion you are saying.
Yes, madam. Not only that one, madam. If for filters, you are IS1A, madam. After routing filter, RMS value of supply current becomes IS1A, madam. But they are taking as IS1, madam, only.
No, it will depend on the application, right?
Means it
If I am
filters.
if I am consuming only active power of the active part of the current, then only I will use IS1A. If I am doing only a harmonic compensation, so in that problem which you have asked, there is a we are compensating only harmonic part, right? We are not taking care of reactive part. So since I am taking care of for me only harmonic part, so the current that my source will have to give even after putting the shunt compensator should be IS1, right? It will not be IS1A.
In that sir lecture also given THIS is equal to ISH by S1A, madam. But in that solution they are given ISH by S1, madam, only. But that's why I'm asking, madam.
No, I am not telling you about the THD. I am talking to you about the current that is supplied from the source. So I am trying to tell you that in case of harmonic that high damp filter that problem that you have asked, the
Here the
supply
formula is
current.
taken as THD IS is equal to ISH by IS1A, madam. Means that means what means, madam, that only active component that is also reactive component is done, madam, already. Their THDIS is equal to ISH by IS1A. They in that formula.
So when you are okay, I told you when you asked this comparison, I told you to mention the lecture number and the problem number and then the assignment problem number. Remember, but you had sent only the question that you have problem in. So until you tell me what exactly where you have the problem and I go and look at it, I will not be able to help you out.
Okay.
Okay,
Means
so
my question is, madam, what is the formula for THDIS, madam? In
THG.
your lecturers also give THDIS.
In our lectures, we have used harmonic component by fundamental component, or right?
11th order harmonics, that problem is solved by you, madam. In that they are mentioning ISH by IS1A, madam. In the SR lecturers also like that, madam. That's is the only difference.
Okay, and so in the solutions that they have provided, they are differing. That you are saying
Yes, madam.
that.
Means they are writing IS1 only.
So you need to tell, like you need to talk, mention this on a discussion forum.
Means if you are solving that problem, madam, like same problem, then I will ask confidently, madam. If you, I post also no reply, but I am asking confidently during problem solving, madam also solved same problem. Madam got this answer. Like that, I will post, madam.
So that is the main reason I am not. See, there are some people who are preparing these questions, so they are the best people to answer those questions. That is what I'm trying to tell you. So if I give you some answer and that does not align with what they have thought in mind, they might have had some other thoughts in mind while making the question, or they might have missed some information while making the question.
If you refer that problem, madam, that
And also, I have told you before that we are not supposed to solve or discuss any kind of assignment questions. That is why what I have been doing is I try to look at an assignment and try to solve problems that can help you solve the assignment. But I am not supposed or responsible for discussing the assignments,
okay, okay, madam.
because I don't have any contact with the people who are making these assignments.
Okay, okay, madam.
Okay, so you can write.
Remaining solutions when it will release, madam. Remaining solutions they are only uh, available only up to 7 assignment solutions only, madam. Remaining it will
That also, that part also, those the people who are making the assignments, they only take care of those things also, and
like
they will release it soon. That time they will
okay,
surely
madam.
send you.
Like exam pattern paper, like they also release, madam. Do you don't know how to that pattern will be examination
It
pattern
will be similar to the
for
assignment.
that case
The pattern is always similar to the what assignments you get.
like objective or like fill in the blanks type like that, madam. We are asking.
According to me, objective will be less. Mostly, it will be subjective, like in assignments. And even if they are objective,
Okay, okay.
most of the
Uh,
NPTEL, it's a general thing across NPTEL that they use the same format that they use for assignments.
okay, okay, madam.
So you prepare for subjective. In case it's objective, it's always good for you.
Okay, okay, madam.
Okay.
If you don't have that much of time, madam, subjective, both objective type, subjective type. The pattern like this means I will prepare a objective or a fill in the blanks type.
No, no. See,
Subject.
it will, even if they are giving objectives, you cannot rely on that, because this is a numerical based course. We have solved a lot of numerical problems. More than 50% of the paper is definitely going to contain numericals. They might either be in subjective form or they might be in objective form. So, if whichever form they are, you have to solve the numerical. You cannot escape that. So, the best way to prepare
Okay,
for exam is solve assignments.
okay, okay, madam.
Okay.
Okay,
Okay. So I don't think there is any exam pattern, some kind of thing that they give, but you can try asking them on the discussion forum, so that at least they will tell you whether it will be objective question or numerical or subjective type question that you can ask them. But the best thing I can tell you is you solve the numericals in from sir's lectures and the ones which are given in assignments. So if you practice both of them, I think you will be good to go. And just try to understand the concept. If you understand the concept, you can solve any problem that they give in on this particular topic. So the reason of the motivation behind you, doing good in this course should not be just marks. You should, if you try to understand things better, you will be able to solve any kind of problem. We solve problem only to become better at or better at understanding. So if you understand better, you will be able to solve problems better. If you solve problem by understanding, then you will be able to understand the concept better. It goes to and fro, to and fro. So whenever you solve a problem, try to go back and read the question, that okay, I got this value when I did this, and then you will see another problem. So in Sir, if you look at Sir's lectures, he starts from the very basic question, and then he will take you to very complicated questions. Step by step, from question number 1 to question number 2, he'll add something in the question, new in the question. Then from 2 to 3, he will add something new to that 2 part. Then that step by step, he is taking the level to very difficult questions. So if you follow that process, assignment questions are very simple compared to what questions Sir is taking in the class. So if you match your level with the questions that Sir is taking in the class, you'll be able to understand things better, and also you'll be able to solve any question that comes your way. Okay.
Okay, madam.
Okay. So now we will start the solution for assignment. So this is our ninth numerical session, and in this session we'll be discussing about active power filters. So this is our first problem for active power filter. So in this problem, we have to design a single phase series active power filter for filtering the voltage harmonics in a 200 volt 50 Hz mains system. And in this system, 15% of third harmonic, 10% fifth harmonic, and 5% seventh harmonic are present due to other loads and the source impedance before it is connected to a critical load of 3 kVA, 220 volt, and 50 Hz at 0.8 lagging power factor. If a single phase voltage source converter is used as a series active power filter, calculate A. Voltage and current rating of active power filter, B. kVA rating of active power filter, C. Interfacing inductance of active power filter. Consider the switching frequency of 10 kHz and the DC bus voltage of 200 volts DC with allowable voltage ripple, when allowable voltage ripple is 5% and ripple current of inductor is 10%. So in this particular problem, you could imagine the system to be something like this. So if this is your single phase AC voltage and this is your coupling transformer series filter, this is your secondary winding for the coupling transformer, this is your series active power filter, and then there is this load. And this is a linear load in the given question. IS, VS, let us say this voltage is VF, and the voltage of this, let us say this is VDC, and the voltage across load is say VL. Now we are asked to find the voltage and current rating of the active power filter, the kVA rating, and the interface inductance. But basically we are asked to design this active filter when there is certain harmonics present in the supply system. So the supply system contains, this is 220 volts, sorry. So this is 220 volt 50 hertz system. And in the system we are given the third harmonic component as 15% of Vs. So 15% of 220 volts, which will come out to be approximately 33 volts. And similarly, Vs5 or the fifth harmonic component is 10% of Vs. So it will come out to be approximately 22 volts. And Vs seventh harmonic only is 5% of Vs.
Madam, you can't write this is the 200 volts, madam. If you are writing the 220 volts, 58.
Uh-huh.
If you are writing 200 volts, so is there any problem, madam? Here, single phase series active or filtering the voltage harmonics in here 220, here 200 volts, 50 hertz means, madam.
Can you please repeat your question?
Here you are corrected 220 volts, madam. But if you write 200 volts, is there any problem, madam?
Yeah, the calculations will change now. I have already mentioned here 220 volts. Here I have mentioned 220 volt 50 hertz, no? So this also have to be same, no? I'm talking about the, I cannot, there was a typing error, that's it. Is it clear?
Here bus voltage is 200 volts, madam. Like
Yeah,
here
bus
bus voltage
voltage is
also
200 volts and AC source voltage is 220 volt 50 hertz.
same, that supply is equal to
Yes.
load side voltage.
Now in the first part we were asked to find the voltage rating of the active filter. This voltage rating Vf will depend on the harmonic compensation. So we will find the sum of squares of these harmonic components in order to obtain the voltage rating of the filter. It is 22 square plus 11 square. This will come out to be approximately 41.158 volts. And for the current rating of active power filter, we can obtain it as, I can call it as IF, and it will be equal to, we are given the voltage, the kVA rating of the load. So we can find this filter rating because it's a series circuit, right? So all the IF will be equal to IS. So we can find it by load kVA by the voltage across the source. So it will be 3000 by 220. It will come out to be 13.636 amperes. Okay. This is the voltage and the current rating. Now the B part of this question was finding the kVA rating. So to find the kVA rating of active power filter, it will come out to be approximately S is equals to Vf into If, which will be 41.158 into 13.636, which will be equal to 561.234 volt amperes. And the C part of this question was finding the value of interface inductance of the active power filter. That is LR or LF, which is equal to the standard formula VDC by 4Fs into delta IF. Now I know that delta IF in the question is given as 10% of IS. So this will come out to be approximately 1.364 amperes. So using this value in this equation, I'll be able to obtain the inductance as 200 by 4 into switching frequency is 10 kilohertz, 10 into 10 to the power 3, and delta IF is found out to be 1.364 amperes. So LF will be come out to be approximately 3.667 millihenry. Okay. So this was our first problem. So for the second problem, again a series active filter is used in series with single phase AC supply of 220 volt 50 hertz feeding a diode rectifier used for charging a battery of 240 volt at 12 ampere average current to reduce harmonics in AC mains current and to maintain unity power factor. And we have to calculate the RMS voltage at the input of the diode rectifier, the line current, voltage rating of active power filter, current rating of active power filter, and the volt ampere rating of the active power filter, and value of DC bus voltage of active power filter, and the value of AC inductor of active power filter. Basically, we have to design the whole filter. And we have to consider the switching frequency of 10 kilohertz and ripples in the DC link voltage and inductor current as 5%. So if you look at the diagram of this system, it will again look like the one similar to the previous question. This is my coupling inductor. This is my interface inductor.
Good evening, sir. సార్ ఈ రోజు రేపు అయితే రేపు నుంచి సెలవు సార్. రేపు నేను గుంటూరే వస్తున్నాను సార్. రేపు ఈవినింగ్ ఈ టైంలో ఉంటారా సార్? కలుద్దాం.
Venkat sir, can you mute yourself? So the DC link voltage that is given is VDC, that can be shown here, and this part will be connected to this. So this is the shunt active power filter, and then we have a diode bridge rectifier load. So if this is my diode bridge rectifier load, then it is connected to a RE type of load. I can connect my system to the load like this. Let me say this is R, this is E, so this is a non-linear load. We have already looked at the waveform of this load, right? And this is a series active power filter. This is IS, this is VS, this is VF. Let me call it as LF, and this is VDC. Okay, so in this question, we are given that value of E is 240 volts, and this current that this diode bridge rectifier is drawing is 12 ampere. This is the average current. And we have to reduce the harmonic current. So initially, if I wouldn't put this series active power filter, then the current drawn by the diode bridge rectifier is non-linear in nature, and it has a lot of harmonic components. So I am putting this series active power filter in order to take care of these harmonics that are present. So in order to take care of the harmonics that are present, I want to inject certain voltage that will result in sinusoidal current. And once I am able to, so I want to inject VF to achieve sinusoidal IS. And once IS will be sinusoidal in nature, the diodes D1, D2, D3 and D4. So diodes will be conducting for 180 degree duration. Diode D1, D4 will conduct for pi duration, and then D3 and D2 will also start conducting for another pi duration. That means all the time, when if this is my supply voltage, this is 0, pi to pi, then if during one time period D1 and D4 are conducting, then my load voltage will be plus 240 volts for this duration, and it will be minus 240 volts for another duration. So my voltage waveform would look something like this, right? Now, based on this waveforms, now let us try to calculate the parameters that have been asked in the question. In the first part, we are asked to calculate the RMS voltage at the input of the diode rectifier. Now, we just saw that the load voltage or the voltage across this terminal looks like a square waveform with magnitude plus 240 volt or minus 240 volt, and we have already seen that the RMS value of a square wave is equal to the amplitude. So the RMS value of this VL waveform is 240 volts, right? So the answer of the first part of our question is, that is the RMS value or the RMS voltage at the input of the diode rectifier is 240 volts. Okay. So in the first part of the question, we have been asked about the RMS voltage at the input of diode rectifier. Let me call it as Vp, and this Vp is equals to 240 volts. This is RMS of a square wave, and the amplitude of that square wave was 240 volt. Therefore, it is the RMS value is also 240 volts. Now, in the second part, we have to calculate the supply line current. Now we know that in the system, the average current, if you look at the output power, then output power will be equal to, for a battery and resistor system, the output power will be approximately E into I average. E is the voltage of the battery, that is 240 volt, and I average is 12 amperes. So from that, output power of my system is 2880 watts. Now using that output power, I can easily calculate the supply line current IS as output power P by our phase voltage Vs. So P is 2880 divided by 220. This will come out to be approximately 13.091 amperes. Now, in the C part, we were asked to calculate the voltage rating of the series active power filter. So, voltage rating of series active power filter, that is denoted by Vf. So, Vf is equals to, we know that the waveform is symmetric for pi duration, so I will find the RMS value only for pi duration. And it is peak value sine theta minus EMF value, since it's RMS value, square d theta, and integration from 0 to pi. So this is the formula for RMS value. And why are we subtracting? We had just discussed, right? This is my Vs, this is my Vf, and let me say this is my VL, or let me say for a battery load, this is my E. So Vf is equals to Vs minus E, and Vs is Vm sin theta minus E, right? And E in the question is given as 240 volts. So therefore, in order to find the RMS value of Vf, I am squaring this expression and integrating it from 0 to pi. And once you do that integration, you will be able to obtain Vf as 104.53 volts. Now, the D part of the question was finding the current rating of the series active power filter, which is equal to IF, which is equal to IS, because it's a series circuit. So it will be equal to 13 amperes. Now, in the E part of the question, we were asked to calculate the volt ampere rating of the series active power filter, which will be equal to Vf into If, and Vf is equals to 104.53 into 13.091. So volt ampere rating of the system will come out to be 1368.407 volt amperes. Now, in the E part of the question, we are asked to find the value of DC bus voltage. Of active power filter. Now, we know that from the expression of modulation index, we can calculate the DC link voltage as root 2 Vf, maximum value of the filter, divided by modulation index. So the maximum value is calculated by multiplying the VF by root 2. VF is equals to 104.53, and let us say the modulation index we assume always is 0.8. So the value comes out to be approximately 200 volts. So we will set the DC link voltage as 200 volts. And in the last part, we were asked to calculate the value of interfacing inductor. And the expression is standard VDC by 4 VF into delta IF. Delta IF is equals to, it was given as 5% of IS. Using this, we could find, we solve this expression, and we could find Fs is given as 10 kilohertz, and this is 0.05 into IS. IS is equals to 13.091. So by solving this expression, you will be able to find LF as 7.639 millihenry. Let us move on to the next question. So in the next question, we have been asked to calculate a series active filter. A series active filter is used to reduce the harmonics in series AC mains current and to maintain almost unity power factor in the series of single phase AC supply of 220 volt 50 hertz feeding a diode rectifier with a capacitive filter of 2000 microfarad and resistive load of 10 ohms. The DC bus voltage of the load is decided to result in minimum injected voltage of the active power filter. Calculate the RMS voltage at the input of diode rectifier, line current, voltage rating of active power filter, current rating of active power filter, VA rating of the active power filter, DC bus voltage, and the turns ratio of the coupling transformer. So in this question, which is given, we have been given certain details, and the special part about this problem is that we have been asked to calculate the minimum injected voltage of the rectifier. So we need to, this is something different from what we have been initially so far. Minimum point was not mentioned. So using this information, let us first start by drawing the diagram again. So again we have this coupling transformer. There will be this interface inductor LF. This is my full bridge topology of series active power filter. Then there is a load which is connected through these terminals, and the load is a diode bridge rectifier. This is again a non-linear load, and this will be connected across these terminals like this. Now this is a 220 volt 50 hertz system. Let me call it as VS. This is IS. Let me call this as VF. This is VL. And the capacitive filter is 2000 microfarad, and the resistive load is 10 ohms. The DC bus load voltage is decided to be minimum. We need to find VF minimum, and we need to find rest of the other parameters. So in this question, let us assume that VF minimum is equals to X. That is X volts is the DC bus voltage of rectifier load. Let me assume that X is the minimum voltage, okay? So VDC is equals to X, okay? So this VDC is equals to X is obtained corresponding to minimum value of Vf. That is the condition that is given in the question. So, in order to start for this equation, let us first write down what will be the expression of Vf. So, Vf is the RMS value 1 by pi, integration from 0 to pi, again it will be 220 root 2 into sine theta, minus we have written the DC link voltage as x square d theta. So this is our expression for Vf. Now I need to find the minimum value of this Vf. That means I'll have to do the integration and then I will differentiate dVf with respect to ds and equate it to 0. And by doing this, I will obtain the value of x as 2 root 2 by pi into Vs, which is 0.9 into Vs, which is equal to VDC. And the value of this 0.9 into Vs will come out to be, this value will come out to be 198.07 volts. Okay, and we'll be deriving this expression in the later problem. So you can, in case you are having problem with the derivation, you can look there. Now, we have been asked first of all to find the voltage that is obtained at the point of common coupling, or the RMS value of the point of common coupling voltage. Now again we know that it's a DC link and it will be a square waveform, and the RMS value of square wave will be equal to 198.07 volts. Okay. In the B part, we were asked to calculate line current at unity power factor, which will be equal to IS, which will be equal to P by Vs. So we need to find the active power. Active power can be directly written as VDC into IDC. We already have the VDC link voltage and the DC link current. We can find out, and we divide it by voltage. So VDC we already know, it is 198.07 volts. IDC is equals to VDC by R, which is equals to 198.07 by 10 ohms, which will be 19.807 amperes. So this VDC into IDC is 198.07 into 19.07 19.807 by Vs is equals to 220 volts. So this will come out to be 17.833 amperes. So this is the value of Is. Okay. And in the third part, we will ask to find the voltage rating of the series. Vf, voltage rating of the active power filter, which is equals to, again, the RMS value 0 to pi 220 root 2 sine theta minus the value of x that we have obtained, 198.07 square d theta. And now we can actually calculate it. So this expression will come out to be 95.752 volts. The next part is current rating of the active power filter, that is IF, which is equal to IS, which will be equal to 19.807. Sorry, IS is equal to line current, which is 17.833 amperes. The E part is finding the kVA rating. kVA rating of series active power filter is equals to Vf into If, which will be equal to 95.752 into 17.833, which will give me 1707.545 volt amperes. In the F part of this problem, we were asked to calculate the DC link voltage, the DC bus voltage, which we have already calculated, which is equal to X, which is equal to VDC is equal to 198.07 volts. And in the gth part, we are asked to find the turns ratio of the coupling transformer. So turns ratio, in order to find the turns ratio of this coupling transformer, this is my source, this is my load, this is my supply side, and this is my voltage source converter side, right? So in the supply side, I already found out the voltage is equal to Vf. Okay, so V supply side is equals to Vf. Now we need to find the voltage source converter side. So for the voltage source converter side, the maximum AC voltage can be found out using DC link voltage. VDC by root 2, that is 198.07 by root 2. So the AC voltage is maximum by root 2, which will give me 140.056. So using this value, which is VF came out to be 95.752 volts. Using these two voltages, we can find the turns ratio N voltage source converted by N supply as V voltage source converted by V supply. And V voltage source converter is 140.056 by V supply is 95.752, and this ratio will come out to be 1.463. This is how you can find the turns ratio of the coupling transformer. And here will be our active series power filter or series active power filter. So let us move on to the next problem. So in this problem, we have been asked to find or to design a three-phase series active filter for filtering voltage harmonics in a 415 volt 50 Hz AC mains, which is having 15% fifth harmonic, 10% seventh harmonic, and 5% 13th harmonic. These harmonics are present due to other loads and source impedance. Before it is connected to a critical linear load of 30 kVA, 415 volt 50 Hz at 0.8 lagging power factor. If a three-phase voltage source converter is used as series active power filter, calculate the voltage and current rating of active power filter, kVA rating of active power filter, interfacing inductance, turns ratio of the coupling transformer. Consider the switching frequency of 10 kHz, DC bus voltage of 200 volts, DC with allowable voltage ripple in 5, which is 5%, and ripple current in inductor is also 5%. So if you look at the diagram for this particular configuration, then this is, since this is a three-phase system, sorry, so let me call this as VSA, VSB and VSC, and let me these are the primary windings of the coupling transformer, and then they all three of them will be connected to a load that will be three phase, three wire linear load. Okay. Now, to the secondary of these coupling transformers, let me say, let three-phase voltage source converter is being used. So, if I have a three-leg converter here and it is connected to a DC link voltage maintained with a capacitor VDC or CDC, and secondaries of all these will be connected, and primaries will be connected to these. And capacitors will be filter capacitor and inductor will be here. LF will be present, right, in all three phases. LF, LF. Okay. So this is our series active power filter. So our system would look something like this. This is our VF voltage, VFA, VFB, and this is VFC, and our load voltages respectively. And this is since ISA, ISB, and ISC. So now in this particular question, we have been given a lot of parts, and in that, so first of all, we know that since it's a three-phase system, we are given the line voltage as 415 volts. So we know that the phase voltage is equals to Vs is equals to 415 by root 3, which will come out to be 239.6 volts. And the system frequency is 50 hertz, and harmonic voltage in a load is 30 kVA load at 0.8 lagging power factor, and the DC link voltage is given as 200 volts, and switching frequency is 10 kilohertz. So let us first calculate all the harmonic components that are given. So we know that the load current is equals to load current or line current is equals to, since it's a 30 kVA load, 30 kVA load, and since the phase voltage is 239.6, so my line current or load current will be approximately 41.736 amperes. Now, ripple current of inductor is given as 5% of IS. This will come out to be approximately 2.087 amperes. And delta VDC is equals to 5% of VDC, which is equals to 10 volts. So VDC minimum will be equal to 200 minus 10, that is 190 volts. And based on the phase voltage, Vs5 is equals to 15% of Vs, which will come out to be 35.94 volts. Vs7 is equals to 10% of Vs. So this will come out to be 23.96 volt. Vs11 is equals to 7% of Vs, which will come out to be 16.77 volts. And Vs13, which is the last harmonic, is given as 5% of Vs. It will come out to be 11.98 volt. So as I have told you before that as the harmonic order increases, the magnitude decreases. So with increasing harmonic order, magnitude is decreasing. Now, in the first part, we were asked to calculate the voltage and current rating of the series active power filter. So, we know that the voltage rating of series active power filter is given as under root of Vs5 square plus Vs7 square plus Vs11 square plus Vs13 square. And this will come out to be approximately 47.86 volts. Similarly, current rating of series filter is equals to IF, which will be equal to our load current or source current, which will be equal to 41.736 amperes. So this is our A part. In the B part, we were asked to calculate the kVA rating. Of VSC of active series filter, which will be equal to Vf into If, which will be approximately, sorry, it's three phases, and this will be 3 into Vf into If. It is 3 into Vf came out to be 47.86 volts into If is equals to Is, which is equals to 41.736 amperes. And this quantity comes out to be 5.992 kVA. For the C part, we were asked to calculate the value of interfacing inductor. So interfacing inductance value that is LF is equals to, there is a standard formula, turns ratio of voltage source inverter by turns ratio of supply side into under root 3 by 2 MA into VDC by 6 AFS into delta IF. So for this expression, we have MA equal to 0.8, VDC we already know as 200 volts, overloading factor is 1.2, switching frequency is 10 kilohertz, delta IF is equals to 5% of Is, which is given as 2.087 amperes, and NVSI by N supply we'll be calculating in next part, so we can put the value then, and then you can come back to this part and write toward the value of LF. So in the D part, we will ask to calculate the turns ratio of the coupling transformer. Which is NVSI by N supply, which will be equal to VVSI by V supply. Now we know that V supply side is equals to Vf, which is equals to 47.86 volts. Now we want to calculate the VVSI. Now we know that the VVSI is equals to the maximum AC voltage on AC side of voltage source converter, which is given by M times VDC by 2 root 2. And M is 0.8, VDC is 200 by 2 root 2, which will come out to be approximately 56.57 volts. So we can say N VSI by N supply will come out to be approximately VSI is 56.57 by 47.86. So 56.57 by 47.86 is approximately 1.1819. So this trans ratio factor, when you use in the interfacing inductor equation, the value of interface inductor will come out to be approximately 1.498 millihenry. You can solve and check it again. So this is how you tackle these kind of problems. Now again we have a problem where we are given a three-phase system, a three-phase 400 volt 50 hertz system is given, and the system has a 6-pulse diode bridge rectifier with a DC capacitor filter feeding a DC of 540 volts at 120 ampere average current to a variable frequency voltage source inverter fed induction motor drive. A three-phase series active filter consisting of voltage source converter with AC series inductor, coupling transformer and DC bus capacitor is used in series of this rectifier inverter system to reduce the harmonics in AC mains current, almost to maintain unity power factor and to regulate the DC bus voltage of rectifier to 540 volts. Calculate the RMS line voltage at the input of the diode rectifier and calculate the kVA rating of the active power filter. So in this particular problem, we have a 6 pulse diode bridge rectifier, and this particular diode bridge rectifier is connected. The output of this 6 pulse diode bridge rectifier will go to a variable frequency drive. Let me call it as VFD. So the DC bus voltage is 540 volts and it is giving an average current of 120 amperes. Okay, so this is my load. Now a series active power filter is to be put in series in order to maintain the unity power factor and regulate the DC bus voltage of rectifier to 540 volts. So in order to do that, we need to calculate the RMS line voltage at the input of diode rectifier. So now we know the expression for the input voltage to the diode bridge rectifier with respect to the DC link voltage at the output, and we know the DC link voltage as 540 volts. So the output waveform for these diodes will be something like this, right? Stepped waveform basically. So from that stepped waveform, this is for the phase voltage. And when we calculate the line voltage by subtracting these phase voltages, the waveform for line voltage will be a quasi-square wave. And we already know how to find the value of a quasi-square wave. So if we draw the waveform of the voltage at the input of this diode bridge rectifier at the point of common coupling, this is the point of common coupling. So VPCC line voltage is approximately equal to, the RMS value of this line voltage is approximately equal to 2 under root 2 by 3 into VDC. We have already calculated since it conducts for 2 pi by 3 out of the pi interval, so it is 2 pi by 3 by pi. So we have already done that calculation of finding this RMS value for quasi square wave. You can look up that calculation if you have any doubts again. And we know that the VDC link voltage is 540 volts. This will come out to be approximately 440.908 volts. So this is the value of RMS line voltage at the, this is RMS line voltage at the input of diode rectifier. Now the second part of this problem is calculate the kVA rating of the active power filter. So in order to calculate the kVA rating of this active power filter, we know that we have to find Vf and If. Okay. Now Vs, that is the phase voltage, is equals to the line voltage by root 3, which is equals to 230.94. And in order to calculate Vf first, we know that this is a stepped waveform. So stepped waveform has 3 steps. So from 1 by root pi, from 0 to pi by 3, 230.94 into root 2 sine theta minus, it will be, this is basically VDC by 3. So we know that the stepped waveform, this one step is VDC by 3, this step is 2 VDC by 3, and this is again VDC by 3. So 0, pi by 3, 2 pi by 3 and pi. So from 0 to pi by 3 the amplitude is VDC by 3, from pi by 3 to 2 pi by 3 it is 2 VDC by 3, and from 2 pi by 3 to pi, it is VDC by 3 again. So considering this pi interval, we have these, so 540 by 3 is 180. So therefore we are directly using this expression. So this is the first part. Then from pi by 3 to 2 pi by 3, again we can write it as 230.94 root 2 into sine theta minus 2 VD by 3 is 360 square d theta, plus third part is from 2 pi by 3 to pi, which is the last part. 230.94 root 2 sine theta minus 180 square d theta. So this is my complete equation. So in order to solve instead of solving the whole thing together, let's solve one part. Let us solve it in a generalized fashion. Integration theta 1 to theta 2, 230.94 root 2 sin theta minus, let me call it as x, because this is varying. Sometimes it is 180, sometimes it is 360. So I am solving it in a generic sense so that I can use it in all three parts. So when you expand this a minus b whole square as a square plus b square minus 2ab and do the integration, you obtain the expression as 230.94 square theta 2 minus theta 1 minus sine 2 theta 2 minus sine 2 theta 1 by 2 plus x square into theta 2 minus theta 1 minus 653.19 into x into cos theta 1 minus cos theta 2. So when you calculate, so this is the expansion of this. Let me call these parts as first, second, and third part. So this is my first part, this is my second part, and this is my third part. Okay, so I made a generalized expansion for all these three parts here, which is in terms of theta 1 and theta 2, and then for the first part I know that theta 1 is equals to 0 and theta 2 is equals to 0 to pi by 3, right? So by keeping the value of theta 1 and theta 2 as this, and x is equals to 180 volts. So by keeping this value, this expression after solving, let me call it as expression y. Okay, so this y1, so y1 comes out to be 7898.59. Similarly, for second part, theta 1 is equals to pi by 3, theta 2 is equals to 2 pi by 3. So y second part comes out to be approximately 2, and sorry, x is equals to 360 for this part. So it comes out to be 2606.86. Similarly, for the third part, theta 1 is equals to 2 pi by 3 and theta 2 is equals to pi, and x is again equal to 180 volts. So y for third part comes out to be approximately 7898.59. Now we know that the expression of Vf is equals to 1 by pi under root of y1 plus y2 plus y3. When you add all these three and divide by pi and take the square root, the quantity will come out to be approximately 76.538 volts. Okay, and this is Vf. Now we know that If is equals to Is, which can be found out by first of all finding the active power and dividing it by 3 times Vs or V phase. So active power of the output of the system is equals to VDC into IDC. We know that VDC is equals to 540 volts, IDC is equals to 120 amperes. So this comes out to be 64800 watts. Using this, I can find IF is equals to IS as 64,800 by 3 into Vs. We know that it is 230.94 volts. So this will come out to be approximately 93.531 amperes. Now we know that kVA rating of series filter is equals to Vf into If, which is equals to 76.5.
Madam, here after designing unity power factor, madam, you are writing IS or IF.
Sorry?
Here IF is equal to IS is equal to P by 3 into Vs, madam. But generally we are writing P by 3 into Vs into cos pi, madam. Means it is designed for unity power factor, madam, already.
Yes, yes. In the question it is given for unity power factor.
Okay.
We are designing for unity power factor. It is not already in unity power factor. So this KVA rating comes out to be 21.474 kVA. This is how we can find the kVA rating. So this particular derivation has been used in many equations. It's a lengthy derivation, but it's a straightforward derivation. So if you're able to solve this, you can practice this numerical and you can find the values. So maintain unity. It was given here, right? Maintain unity power factor. Right? And another important problem was that minimum value one, where you have to differentiate this. So when you differentiate this one, which problem was that? Yeah, this one. Minimum injected voltage. So we have to differentiate Vf with respect to x and equate it to 0. When we do that, the value of x will come out to be something. And that value of x will be our DC link voltage x. Okay. So these were the few important questions from the topic of active series power filter. Any doubts from the topics that we have covered today or before?
Madam, I have a small doubt, madam, in sorry video lecture.
Okay.
Second problem in that power
In the
filter,
There's an
active
active
series power
series
filter.
power filter only.
Yes, madam.
Okay.
This is, madam, single phase VSA with square wave AS output of 220 volts RMS.
Yes.
A single phase VSI with square wave AC output of 220 volts RMS at 50 Hz
Mm-hmm.
is feeding a critical linear load of load value, madam, 4 kVA, 230 volts, 50 Hz, 0.8 lagging, madam.
Okay.
Single phase series active filter is used to in the system to eliminate the voltage harmonics to regulate the fundamental 230 volts RMS across the load, madam. In that SAR problem is 220 volts. Here the difference is 230 volts, madam. How to derive that VF value, madam?
VF value, it is given, right?
Means here the square wave AC output, madam. Here a single
Uh-huh.
phase VSA with square wave AC output.
Uh-huh. So you will do opposite, right? Since in this problem your Vs is equals to, if you look at pi interval, then it is equal to 220, right?
Yes, madam.
And
Square wave 220 volts RM.
and your load voltage will be sinusoidal. So you can call it as 220 root 2 into sin theta.
Here the load 230 volts given, madam.
Load given as
230 volts, madam.
no, it is given as 220 only. Both are given as
Madam,
220. I have question in front of me. It is given as 220 only. So 230 value is not given.
if there if 230, 240 is like given, madam. Like 230,
The procedure
if
will
load
still
is
remain the same. Procedure will still remain.
madam.
You will just replace this 220 with 230 or 240, whatever is given in the question. Basically, here
Okay,
what
that
is
what is the
happening
load operating voltage value? Load which is operating value?
is you are given source voltage as square in this question, right?
Yes, madam.
Source voltage waveform is square. This is source voltage.
Yes,
And load
madam.
voltage is sinusoidal.
Science
So
order. Okay, okay, madam.
whatever is the peak voltage of this load voltage, whether
You
it
are
is
telling
230
up to this in this session only reverse in that reverse, madam. That's why I'm asking, madam. That is
yes,
the
yes. Here
only
it is
doubt.
only yes. Here only it is reverse. So that is, but still it will be again. This is our Vs, this is Vf, and this is Vl, right? So again it will be Vf is equals to Vs minus Vl. So we'll again use the same formula only. Only this time Vs is fixed and Vl is sinusoidal. Till now Vs was sinusoidal and Vl was fixed. Okay. So only that will change. Apart from that, everything else will remain same.
Okay, okay, madam. Thank you, madam.
Okay. Any other doubt?
If you VL is to okay, no doubt, madam. No doubt, madam.
Okay. Then we'll end today's session.
If you VL is equal to 230 means if you write 230, that's all, madam. If you're
Yes.
operating 230 volts,
Yeah. If
don't
peak voltage is suppose this VL magnitude is 230 into root 2, then I will just
yes, yes,
replace this 220 by 230.
230 just
So it
okay,
will
okay,
be V peak. Suppose V peak is the amplitude of this square wave. V peak minus Vm sin theta square d theta integration 1 by pi square root. This will be Vf.
yes.
Okay. Okay, so then we'll end today's session. Thank you for attending the session. We'll see you next time. In case you have any doubts, you can, as usual, mail me. And if you still have that doubt in the question from assignment 8, you can, if you want to compare, then you can tell me the lecture number and question number, then I can try to find out what the issue is. Okay.
That question number 8, madam. Already posted, madam. That one.
The lecture, you told now that sir has also done the same problem in the lecture, and in the compare at both the places the formula used is different. That
That
part.
is the only I posted to you, madam. That is the only I posted the same. Whatever the sir told. Question number 8 in that
You have sent
I already
assignment question. I am asking you to send which problem number from lecture of NPTEL is similar to that problem and the formula used is different. That problem that I am asking. I know which question you have doubt in, but I don't know which question in lectures are you comparing it with.
okay.
Okay.
In that week already we already written, madam, clearly in that one. Okay.
You have given me a question, and that question is same as assignment 8 question. But in the lecture, which lecture number, which question
No,
number?
that is 8 question. That video lecture is 8 question, madam. That all I posted that assignment question, madam.
Okay, and which lecture is it?
Uh,
Lecture number.
1 minute. Okay, 1 minute, madam. In week 6, madam.
Sorry?
For filters, madam. In week 6.
In week 6, there are 4 5 lectures, right? You can just write, find the lecture number. That is what I'm trying to tell you. Otherwise,
Positive
I'll have
power
to
filters, positive power filters continued, madam. First one. I already also mentioned that one, madam.
passive
Passive
that's
power
fine.
filters.
Okay.
In that eight question.
Okay. I'll try to look into that. But meanwhile, you also post it in the discussion forum if you haven't posted till now, and you can also ask if you have any email ID of NPTEL people so that they can tell the TAs to reply to the discussion forum quickly. You can mention that in the discussion in your feedback form or wherever you can contact the NPTEL people. They will ask the TAs to be active with the discussion forum. Otherwise, you will have problems.
Okay, how to? I were unable to contact the discuss forum, madam. No response to discuss
That
forum.
is
That's
what I'm
why.
trying to tell you that you have to inform this to NPTEL people so that they can make the TAs reply on time.
Okay, okay, okay. Means already posted in NPTL, madam. Helpline. They are saying that they are interactive in slowly. It means they will communicate you slow manner like that. They are responding, madam.
Okay. So then you will have to wait for some time maybe. They will definitely respond before the exam, so that part they will take care. Don't worry.
Okay, okay, madam.
Okay. Okay.
Okay, thank you, madam.
Okay. Thank you. Bye.
Okay, okay.